In this video, we are going to have the three descriptions of f of a. First, f of a, we are going to have it as the intersection of all subfields of k containing f and a. So that is one description, or in other words, it is the smallest field containing both f and a. So one description is f of a is the smallest field containing both f and a. Then another description is we have k to be extension of f, k to be extension of f. So when I consider an element say a in k, a can satisfy a polynomial or it is not root of any polynomial. Now suppose a is not a root of any polynomial over f, then in this way f of a is described, collection of all quotients f of a by g of a. We can call it as small f of a by g of a. It's an expression in a algebraic expression, and similarly in the denominator with the denominator non-zero. Or we can simply say f of a is this collection with beta not equal to 0. So this is the case if a is not a root of any polynomial over f. Now suppose a is root of minimal polynomial, and that minimal polynomial is of degree say n, then f of a will have this form. So this is orally, if you want to say what is f of a, it is the smallest field which contains both f and a. But when you do problems, when you know that a satisfies minimal polynomial of degree n, a may satisfy any number of polynomials, but of all the polynomials satisfied by a, there should be one with the least degree. So the degree of that, if it is known, that is say 3, then in that case f of a, suppose you have degree of n is 3, then in that case f of a will be alpha naught plus alpha 1 a plus alpha 2 a square. So you have the explanation and all we will have in detail only in the next video. Here we are only describing what could be our f of a. So here the basis concept and all will come, that is degree of f of a over f in this case. Because it satisfies a polynomial of degree n, that is 3. So here you have 3. It should have basis consisting of 3 elements, and that those basis elements are 1a square. So all that in theory that we are going to have in the next video. So here just an introduction that have and all your f of a will appear in the book. So it is the smallest field containing f and a. Another description, if it is not a root of any polynomial, then this quotient form that it will take. And if you have this f of a, I mean a is a root of a polynomial of least degree, namely n, then in that case description for f of a. This is very important when we do problems, this kind of description. The reason is, suppose you want to express, see, you know that root 2 satisfies this polynomial x square minus 2 over q. So you want to know what is q of root 2. So how will you express that? So root 2 satisfies this. Suppose when you have in the place of a, you have root 2. So here we said that 1a square, if you have 3 to be the degree, and here the degree is only 2, so 1 and a, which means you will have alpha naught plus alpha 1 a, but a is root 2. So you have these scalars ranging over q. So this is the description of q of root 2. So like that, to describe what is the given collection, this q of root or whatever it is, say q of cube root of 5, in that case what is the minimal polynomial this element a satisfies, that you must see. So we can easily say that it is x cube minus 5. So in that case, then how will I express my q of cube root of 5? So for that purpose, this description is very much needed. So one is, it is the smallest, this is the basic definition, it is the smallest field containing f and a, and this one is useful when you do problems. So we will see the definition of field adjunction. What is the meaning of field adjunction, that we will see, and what do you mean by A belonging to K to be algebraic over F and algebraic of degree N. So all these will be discussed in this section, but as far this video is concerned, we have the description of f of A to be the smallest subfield of K containing f and a. What is K? K is the extension of f. And remember, when you adjoin A to F, naturally A should not be there in F. If A is there in F, why do you adjoin that? So it is it should be known clearly that A should be only in K, not in F. So let script M denote the collection of all capital M, where capital M is a subfield of K containing F and A. That is, collection of all subfields of K containing F and A. Since K itself is a subfield of itself, it contains F and A, so this collection is non-empty. And you describe your F of A as the intersection of all these subfields. So these are taken from this. So let E be any subfield of K containing F and A. Then intersection. This is intersection means it is the smallest subfield of K containing F and A. So what is that you have? F of A must be contained in E. So it is the smallest subfield of K containing both F and A. Containing both the F and A. So in this case, we say that A is adjoined to F, and the process of adjoining A to F is called field adjunction. This is what we said. If A is not a root of any polynomial, if it is a root of some polynomial, at one point this will become 0. We don't want this expression to be 0. I mean, to contain 0. Whenever you have quotient form, it is natural to describe the denominator is non-zero. So for that reason, you should not have A to be a root of any polynomial. So let K be an extension of F and A belong to K, and U be this collection. M and S are non-negative integers, and alpha i's and beta i's are non-zero scalars. Non-zero scalars, especially we do not want beta not to be 0. It should not be 0. Now we are going to establish that this U and f of A is the same. So f of A contains both F and A and is a subfield. So like that we are going to have, what is that, U is actually f of A. That is what we are going to prove. So first we know that U is non-empty, because when you take alpha naught and beta naught 1 and the rest of them to be 0, alpha I, if we have them to be 0, this is J. For J ranging from 1 to S. Now U is non-empty because this is present, because these are elements, alpha i's and beta i's, they range over capital F, scalars. So it is non-empty, and you consider two elements to show that it's a subfield. We need to show that with regard to addition, this condition, and with regard to multiplication, this condition. So two elements, we shall take them as X and Y, F of A by G of A, H of A by R of A. R of A non-zero, G of A non-zero. When you consider X minus Y, when you take LCM, this is what you get. There will be again an expression in A, and in the same way in the denominator. And the denominator is non-zero because both the R of A and G of A are non-zero. So this x minus u y is a member of u because it is of the form for it to be an element in capital U. Now we want to find, we want to prove the second one. So we shall take x as this and y as this. Here y should not be 0. For y to have inverse, it should be non-zero. That's the definition of a field. All the non-zero elements should have multiplicative inverse. So it should be non-zero, which means both numerator and denominator, both of them should be non-zero. Both of them should be non-zero. So when you consider xy inverse, this is what you get. And again, this is some L of A and this is some N of A. So you have this implying xy inverse belonging to U. Therefore, U is a subfield of K. Obviously, U contains both F and A. Now, actually, this proof not given in Herstein, as for examination point of view is concerned, it is not at all needed. But still, just to know that it has got various description, this is discussed. Right now, use a subfield of K containing both F and A. Since F of A is the smallest subfield of K containing both F and A, use any other. The smallest must be contained in any other. So you name that as statement P. Now, do we have U to be contained in F of A? Now, since F of A contains both F and A and is a subfield, all these collections will be in F of A. Again, as F of A is a subfield, that is known already. That is how it is introduced. It is the smallest subfield containing both F of A, both F and A. So this collection should also be there in F of A. So U must be contained in F of A. Here U must be contained in F of A. This is what we are trying to prove, and that is established here. So you have U to be equal to F of A. So again, let me say that this is not from the examination point of view, just alternate description that it has got. But we will be proving when A is the root of minimal polynomial, then minimal polynomial whose degree is n, then F of A has that description alpha naught plus alpha 1A, or these are scalars, they can be even beta naught. So and so on, alpha n minus 1. This is very important. This result is very important. So this will not be asked, right? Now this F of A is called a simple extension of F. You have F and you are adjoining A, which is not an element in F, to this F, and so you have F of A. This is called a simple extension. This is called a simple extension. So in the next video that we will have, this is an important theorem. A is algebraic over F if and only if F of A is a finite extension of F. So for that some preliminary results are needed. So that will be discussed, and with the help of them this theorem will be established. That will be in the next video. And when you have A to be algebraic of degree n, A satisfies a polynomial over F of degree n, but no non-zero polynomial of lower degree. It should be of least degree. So here only, if A belongs to K is algebraic of degree n, then degree of F of A over F is n. So in the course of this proof only, we are going to have the expression. We will be introducing T as this, and we'll be establishing that T is nothing but F of A. So this will give the alternate another description of F of A. So in this video, our aim was to describe F of A. One is the definition. It is the smallest field which contains both F and A. The process of adjoining A to F is called field adjunction. That is the definition. Smallest field containing F and A. And if A happens to be root of some polynomial of degree, least degree n, then your description of F of A is this. And if A is not a root of any polynomial, then the description of f of a is what we expressed here, this one. So this is what we wanted to convey in this video. Thank you.